Good morning, class. This is Tausi Khanwa from Assistant Professor Civil Engineering Department, and I'll be dealing with mechanics of material for you in the semester. And we all know that this subject is the extension for your subject which you have studied in the previous semester, that is solid mechanics. So basically what we have in the first unit is deflections and slopes. Deflection and slopes. This is your unit 1. We will be studying slope and deflection applied on different conditions of a beam with different types of loadings. So consider, we'll start with the unit here. Consider a beam which is subjected to some sort of loading. Let the beam be simply supported at the ends. Both the ends are simple supports. So this is the deflected profile. If I draw this as the deflected profile here, of course this is exaggerated one. This type of deflections won't be occurring. These two are the simple supports. They don't allow any deflection. Application of the load, the beam will deflect here. So deflection, it is defined as the vertical displacement of beam due to applied load. Okay, so it is denoted by small y, and y is the deflection here, which is maximum in this case at the midspan. So it is denoted by y. On application of load, this is the deflection occurring. It is denoted by y. At any point, if you calculate, it is called as y. Now next is slope. If I draw a tangent to this deflected profile, the angle measured between this beam and the deflected and the tangent drawn, it is given as theta. So theta is denoted by theta. It is defined as the angle made by the deflected profile and the tangent drawn. So if I draw a tangent, this is the theta which I am measuring on this left end. Similarly, if I draw a tangent on the right side, this is the angle which I am measuring, which is theta. So slope can be calculated at both the ends. The slope, generally in this case, the slope is 0 at the midspan. Next is we have 4 methods to calculate slope and deflection in beams. So those methods are the first one is double integration method. Second is Macaulay's method. Third one is moment area method. And the last one is conjugate beam method. So these are the 4 methods to calculate slope and deflection in beams, which are so can be calculated by using these 4 methods. Of course, all the methods have their own limitations. So based on the limitations they were developed, this is the first method, double integration method, whose extension is Macaulay's method, and these 2 methods are different methods. So first we'll start with the double integration method. Double integration method. Double integration method, by the name you can understand, it is integrating twice. 2 times you need to integrate, so slope and deflection can be calculated. So in this equation, we have a governing equation. You have a governing equation in this method, which is given as, there is a governing equation which is given as ei d square y by dx square is equal to mx. This is a differential equation. Ei d square y by dx square is equal to mx, where E is given as Young's modulus or modulus of elasticity, which you have studied in the solid mechanics. It is for different for every material. I is moment of inertia, depends on the section, and d square y by dx square is a differential equation. This is equal to mx. Mx, it is defined as bending moment about a section, or at any section, bending moment of all the forces taken about a section or at a section. So this is called as the governing equation, which is very important in the case of double integration method. It is given as ei d square y by dx square is equal to mx. Now this equation, if you integrate this one twice, I'm writing this one again, ei d square y by dx square is equal to mx. Integrating twice, so double integration is applied. Integrating twice, this equation will become ei dy by dx, so d square y by dx square, on integration it will become dy by dx is equal to mx. Integration of mx dx, integral mx dx. So this is your slope. On first integration of the governing equation, you will get slope. Theta is given as equal to dy by dx. So theta is equal to dy by dx. So ei theta is equal to integral mx dx. This is your first equation. By first integration will give you slope. If I integrate this one again, ei y, this dy by dx will become y. Of course, you have an integration constant. Always remember, when you integrate any equation, you will have an integration constant. So we'll write the constant as c1 here. And second integration, ei y, this will be double integration of mx dx plus c1 plus c2. You will have one more integration constant as you are integrating one more time. So two integration constants will be there. So this is called as the governing equation, which is ei d square y by dx square is equal to mx. Mx is the bending moment. I'm substituting here the value of mx, and I'll integrate this equation two times. So mx value will be different for all the equations. This is first, this is called as slope, and this is your deflection. So this is the procedure to be followed in the case of double integration method. So this is the method. Ei y is your slope, ei theta is your slope, and ei y is your deflection. Now in this equation, if you calculate the values of this c1 and c2, you will be able to get what is slope and deflection. So how to calculate c1 and c2 is, you need to apply some boundary conditions here. So what are the boundary conditions? Boundary conditions. Boundary conditions we have. Suppose consider a cantilever beam like this, which is subjected to, it is a beam which has one fixed end and one free end. Cantilever beam, it has always one fixed end, one free, and I am applying a point load of W at the free end. So this is the deflected profile of the beam. The beam deflects in this manner, so such that there is no deflection or zero deflection at the free fixed end, and there is no rotation. Remember, this fixed support won't allow any rotation and any deflection. So slope and deflection both are zero at the free end, whereas you have maximum deflection at the free end, and also you have maximum slope at the free end. So, moving on, what are the boundary conditions we have? First, before that, we'll study what is mx. We'll get to know what is mx. So now consider a section 1 at a distance of x from the free end. Always remember, sections are considered from the right end of the beam. To follow this sign convention which I am using, the sections are to be considered from the right side of the beam. The section 1 at a distance of x from right end. Always from the right end, any sort of problem you need to consider x from right end of the beam. So mx, it is the two sign conventions which are followed here is sagging and hogging. Sagging and hogging. So whenever the deflected profile, if you see, suppose you have a simply supported beam which is subject to load, this is the deflected profile of the beam. So this type of deflection is known as smiling face. It is to be taken as positive. Remember the sign convention. For your easiness, I am giving you that smiling face. It is positive. And hogging, if you consider a cantilever beam, the deflection will be like this. This is sad face. So deflections, moments should be taken as negative. Hogging, sagging moments are positive, smiling face positive, and hogging moments are sad face negative. So mx is to be, these are the sign conventions which are to be followed. I'll write here sagging sign conventions for mx. Sign conventions for mx. Sagging is positive and hogging moments are negative. Now moving on, we'll get to know what is boundary conditions first. You remember that boundary conditions are to be applied when to calculate C1 and C2. So I'll write the equation for mx. In this case, you have a point load of W which is at a distance of x. So at free end, if you see, if I move the section at free end, what will happen here is x will become equal to 0. So at free end, x will be 0. Okay, and what about y? Y is the deflection measured here. Y is the deflection at the free end. It is x will become 0, and what about y? Y will be equal to y maximum. We'll have maximum deflection in this case at the free end. So at the free end, x is 0, y is 0. Similarly, at fixed end, if you see, fixed end is at A, x is equal to, now this complete length, x is always measured from the right end of the beam. So if the section if the section is moving towards fixed end, x will be L and y is 0. There is no deflection and rotation at the fixed end. The fixed end won't allow any rotation and any deflection. So x is 0, y is y max, x is equal to L, y is 0. These are the boundary conditions. This is y. Boundary conditions to be used to be substituted in the governing equation. This is y is y max and x is equal to L at the fixed end. Y is equal to, if I move the section towards fixed end, x is measured from the right end, so x will be equal to L and y will be 0. So these are the boundary conditions which are to be applied in the governing equations for the case of a cantilever beam. Next is, we also have simply supported beam. Simply supported beam, case 2, which is simply supported beam. Simply supported beam, consider this case, it is simply supported beam is hinged at both the ends, or hinged and pinned at both the ends. If I apply some sort of loading at the top, the deflection profile will be like this. This is your deflection profile. The beam deflects in this manner. So if I consider a section 1-1 at a distance of x from right end. Always remember section is considered from at a distance x from right end. So at right end, if I move this section towards the end, now let this be A and B. Suppose end A and end B, right end B, you have x is equal to 0. X will become 0 because section is moving towards the end B, it will become 0. And also you don't have any deflection, so y is also 0 there. Deflections at the supports will be 0. Always remember there is no deflection at the supports, so y is also 0 in this case. What about theta? Theta is dy by dx, which is equal to dy by dx maximum. Dy by dx maximum is your theta. Now, similarly, if I move towards the left end, at the left end, what is the left end? That is A. Now x will be equal to L, this complete length of the beam. X is measured from the right end, so x moving towards A, x will be L. What about y? Y is 0. Deflection is again 0 here. No deflection because it is a support there. Now what about theta? Theta is dy by dx, which is equal to dy by dx maximum again. Suppose you have a simply supported beam. Both the cases you have reflection 0 at the ends and slopes are maximum at the supports. Now there is some point where deflection should be there, so zeros are there, deflection for both the ends. So if you see the profile, the deflection is maximum somewhere in the midspan. So if you have a symmetrical loading at midspan, x is equal to L by 2, what is the deflection recorded is y max. Maximum deflection will occur generally in the case of symmetrical beams at the midspan, and for unsymmetrical beams generally it happens under the point of maximum applied load. And what about dy by dx? Slope will become 0 at the point of maximum deflection. So this was the first case of second case of simply supported beam. What are the boundary conditions here? So boundary conditions apply. I'm applying loading simply supported beam. This is the profile. Considering section 1 at a distance of x from C. At right end, if I move the section towards right end B, x will be 0. What about y? It is 0 and theta is dy by dx max. Similarly, if I move the section towards end A, x will be L, y is 0, theta is dy by dx max. This is same in both the cases. What changes here is x. X will become L and x will become 0. Now, for maximum deflection, I am using the midspan. Suppose you see the cantilever beam. In this is the deflected profile. The deflection at the end, fixed end, is 0 because it does not allow any slopes and rotations at the fixed end. So whereas in the case of simply supported beam, you have some rotations here, but the deflection is 0. This is the rotation here. Okay, you have rotations in the beam, but there is no deflection occurring in the beam. So the next one is we'll move towards the problems, that is the case 1, which we will study here. The case 1, cantilever beam subjected to point load at free end. So this is the basic and the first case in which you will be calculating the slope and deflection at the free end for a cantilever beam. Now consider this is your beam. This is the load applied at the free end A, and the length of beam is L. I'm applying load at the free end. So in this case you need to calculate slope and deflections here. So for this, if you remember, we have a governing equation which is I'm considering one section here, section 1 at a distance of x, section 1. So what we have, the governing equation ei d2y by or d square y by dx square is equal to mx. This is the governing equation which is to be used. Now section 1 is considered. I'll write first what is mx. Mx, consider section 1 at a distance of x from, let this be a and this b, this is your free end is b, at a distance x from b or free end. So this is x here. So I need to write the equation of mx. Mx is equal to what is the load you have on the right side? That is, you have a w, which is point load, and the perpendicular distance is x. So it is w multiplied by x. Now see the sign you have. Sign convention is to be followed. This is a sad face bending moment. This is moving downward. So sad face bending moments. This is sad face bending moment. It is moving downward. So this is to be taken as negative. This is hogging bending moment, which is negative. So mx is minus w into x. Now this has to be substituted in the governing equation. ei d square y by dx square is equal to minus w into x. Now what is the procedure to be followed in double integration is, you need to integrate this equation twice. Integrating twice. So this equation will be ei d square y by dx square is minus wx. I need to integrate this one twice to calculate slope and deflection. On first integration, this will be ei d square y by dx square will become dy by dx. Integration of d square y by dx square is dy by dx is equal to minus w into integration of x power 1. It is x power 1 plus 1 by 1 plus 1. So x square by 2. Integration of x square is x square by 2, and you also have an integration constant c1 here. On integration you have a constant c1. So this is, let this be equation number 1. Now second time integration, ei y is equal to ei dy by dx will become y here. It is equal to minus w into x power 2. Integration of x square is x power 3 by 3. So plus c1x plus c2. Let this be your equation number 2. Minus w, x square will be x cube by 3, or x power n by n plus 1. X cube by 3, 2 into 3 will be there. Plus c1x plus c2. This is your equation number 2. Now using these equations, you can calculate slope and deflection at any point when you have the value of c1 and c2. So c1 and c2 can be you can calculate the deflection and slope at any point when you have the values of c1 and c2 here. So c1 and c2 are to be calculated by using boundary conditions. So using the boundary conditions, remember the case of cantilever beam, how the deflected profile will be. You'll have zero deflection at the fixed end and maximum deflection will be there at the free end. So at fixed end A, this is the first boundary condition I'm applying. At fixed end A, x will be equal to L. Okay, and what about y? Y will be equal to 0. Y will be 0 here. So you need to substitute in the second equation to calculate. We also know that dy by dx is also 0 at the fixed end. So we'll substitute in the first equation to calculate c1 first at the fixed end. See, the deflected profile is like this. there is no deflection and rotation at the free end. X is moving towards L. No deflection and rotation at the free end. So x is equal to L, dy by dx is equal to 0. Substituting in the equation number 1. 0 is equal to minus WL square by 2 plus C1. Okay, so dy by dx is 0. X is equal to L, so WL square by 2 plus C1. Or from this equation, C1 will be equal to plus WL square by 2. This is the value of C1 which you got from equation number 1. So WL square by 2. Similarly, you need to apply the second boundary condition at fixed end A again. At fixed end A again you have x is equal to L, y is 0. Deflection is also 0 at the fixed end. So both these cases are at the fixed end. X is equal to L, y is 0. I use this equation in the substitute these values in the second equation by also substituting the value of C1 here. So EIY is 0 is equal to minus WL cube by 6. X is equal to L here. Minus WL cube by 6 plus C1 is WL square by 2 into L. C1 is WL square by 2, x is equal to L, I am substituting here, plus C2. Or now in this equation, this will be minus C2 is equal to, or 0 is equal to WL cube by 3 plus C2, or C2 is equal to minus WL cube by 3. This is the value of C2 which we have got. So C1 is minus plus WL square by 2 and C2 is minus WL cube by 3. Now these values of C1 and C2 are to be substituted back in the equation number 1 and equation number 2. C1 and C2 is to be substituted in this equation number 1 and 2. So you have used boundary conditions to calculate C1 and C2. Use this conditions here and we'll write the equations again. EI dy by dx is minus wx square by 2 plus wl square by 2 C1 here, and EIy will be equal to minus wx cube by 6 plus integration is happening here, the x square is x power n 1 plus 1 plus wl square by 2 into x plus minus wl cube by 3. So the final equations you will get is EI dy by dx is equal to minus wx cube x square by 2 plus wl square by 2. So I am substituting the value of C1 in the equation number 1, and similarly EIy will be minus wx cube by 6 plus C1 is wl square by 2 into x plus minus wl cube by 3. So these are the final equations for a slope and deflection, which if you substitute the values of x at different points in the beam, you will be getting what is slope and deflection in the beam. X is to be substituted from the always measured from the left end. X is always measured from the left end to be substituted in the equations. Now I'll calculate what is the deflection at free end. At free end, you remember we have maximum deflection and maximum slope in the case of simply cantilever beam. At free end, what is x is equal to? What is x is equal to? X is 0. Okay, x at the free end is always 0. X will become 0 at the free end. If I move this section towards end B, x will be 0. X will be 0. Now I'm substituting x is equal to 0 in first equation. EI dy by dx is equal to, this will become 0, WL square by 2, or dy by dx is equal to theta is equal to WL square by 2EI. WL square by 2EI, this is the equation for slope. Similarly, x is equal to 0 in the second equation. EIY is equal to 0, 0 plus 0 minus WL cube by 3. So y is equal to minus WL cube by 3EI. This is your maximum slope at the fixed end, free end. Now we have here is, so somewhere in the in this beam you can calculate deflection and slope at any point. Let us consider at mid span. At mid span, what is x? X is equal to L by 2. So substituting L by 2 in both these equations, EI dy by dx, EI dy by dx, I'll write here, at mid span, x is equal to L by 2. Substituting in this equation, EI dy by dx is equal to, this is minus W by 2 into L by 2 whole square, or L square by 4, plus WL square by 2. This is equal to minus WL square by 8 plus WL square by 2. If you simplify this one, on simplification, you will get what is the slope at EIY is equal to minus W by 6 into L cube by 8 plus WL square by 2 into L by 2 minus WL cube by 3. So again, on simplification, you can calculate the slope and deflection at midspan. EIY is equal to minus WL cube by 6, 8, 48 plus WL cube by 4 minus WL cube by 3. If you simplify this one, on simplification, you can calculate the slope and deflection at the midspan of the beam. So this is EI dy by dx, or EI theta, and this is EIY. Simplify this one. So that's all for the today's class. Thank you.